Now, here's another way of looking at the spectral theorem or its implications. So suppose we've got a self-adjoint operator T, and once again, its corresponding orthonormal basis of eigenvectors. Now let's take a polynomial P and consider the spectral representation of this polynomial, just following what we did in the last clip. So now we're going to take some polynomial of T and apply that to the vector V. And so if I expand V in terms of the orthonormal basis, it's going to look like this guy. And then since this is a linear combination of the EKs with coefficients that look like this, that factors through this linear operator. And so I can just look at the linear combination of that operator applied to each component. So now if I do like a little side computation here and say, okay, so what does it look like if I do P of T applied to EK? Well, P of T looks like, you know, some constant term plus some linear term plus some quadratic term, da-da-da-da-da. And this goes up to some power, let's say m, something like this. And this is all being applied to EK, right? Okay, so let's see. So when we do this one times EK, then we're going to just end up with A0 EK. And then when we do this one times EK, then using the fact that EK is an eigenvalue, we're going to get A1 times lambda EK. So we've got A1 lambda EK. Now for the next one, let's see. So this one being applied to this guy is going to give me A2 times, and then when I apply the T twice, it's going to kick out 1 lambda K for each application. So it's going to be A2 and then lambda K squared EK. And I just realized I forgot to put a subscript on my lambda back here. So let me just squeeze that, whoops, in, sorry, that's a K. There we go. And so on and so forth, A M lambda K to the M E K. And now note that I can factor out all those EKs all the way through. And the thing that's left is actually, so A0 plus A1 lambda plus A2 lambda squared plus da 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 da. That's exactly P of lambda K applied to EK. The plot thickens, right? So okay, so then I can simplify the last line of this derivation over here and say, oh, so that's going to be K equals 1 to N times V E K P lambda K EK. And then following what we did last time, I can write this as the sum over the elements of the spectrum of T, P of lambda times the projection to the lambdath eigenspace applied to V. And so again, this one implies then that T is equal to, or sorry, P of T is equal to this sum. And so that gives us a spectral representation of P of T. Now, if you take an analysis course, there's this very famous result called the Stonewastron theorem. And the Stonewastron theorem says that for a continuous function on an interval, so let's just say f from a to b. So f is a function from the interval a to b to the reals. We can find polynomials so a sequence of polynomials, and so here this is a sequence of polynomials. With the max difference between f and the polynomial on that interval going to 0 as n tends to infinity. Okay, so that's a mouthful. This is and what is this? This is saying that the sequence Pn converges to f uniformly. And so what does this mean? Well, I'm just going to draw a picture and hope for the best. So if this is our interval from A to B, and then we've got some function f, and it's continuous, then what this is saying is that I can find polynomials whose max discrepancy from f is as small as I want. So if I take, say, like epsilon to be this distance right here, then that's like saying I can find a polynomial that will guarantee. I don't know why I made such a horrible, awful function here. Let me do that again. So I'm going to take my function to be like this. Okay, then there we go. All right. So then what the theorem states is that I can find a polynomial whose graph is in this blue zone. And you say, okay, well, that's not a very good approximation necessarily. It could be pretty hairy, whatever that P looks like. But then I say, oh yeah, but you know what? I can also do it for this green epsilon here. That was supposed to be green. And then I can, obviously, so you can take whatever, as fine an epsilon as you want, and you're guaranteed of being able to find a polynomial that matches f everywhere inside that tube simultaneously. That simultaneousness is the origin of the word uniform right here. But anyway, this is a very strong form of convergence, and it makes lots of nifty things possible. So in particular, for such an f like this, this means that we can actually pass it through the sum, and by sum I mean this sum right here, and get that f of t is equal to the summation over the spectrum of f of lambda p lambda. And even for infinite dimensions, f of t can be written as an integral over the spectrum. And so this is absolutely crazy, right? Because what we've just done now is we said, okay, for any continuous function f, I can define what that is for an operator. So things like e to the t, right? Or the square root of t, or cosine of t, or, you know, I mean, that's crazy. I mean, you can put things in here that, you know, aren't even necessarily functions that can be obtained as power series. But just limits of sequences of polynomials. So this is called the functional calculus. And it means figuring, and the functional calculus is an idea for how to apply functions, presumably functions with a numerical input. To operators. And it's a very important part of functional analysis. It makes quantum mechanics run and all sorts of other, well, parts of classical mechanics and other stuff as well.